Yeah, so my name is Mike Benjamin, and I'm here to talk to you about marine autonomy and particularly the open source aspect of it. There's a lot to talk about technically. That's not necessarily the focus today. It's more about how we have structured this project and how we're engaging with users and the issues that brought us here and the things that we're currently dealing with. Um, Quick note right up front, I'd like to acknowledge our sponsors. The sponsors above the lines are sponsors who have funded MOOS-IVP as an open source project explicitly, most notably ONR for the first 10, 15 years, Battelle in the mid 2000s, and more recently NSF. And the open source project has continued to evolve as we've been involved with other projects below the line there with different research objectives, but continuing to grow the software infrastructure. So the key thing we want to talk about today is, at a 10,000 foot level, open source software, which is, code that we put online plus a suitable software license. Does that necessarily equal industry adoption? And I should mention that industry adoption is not why we started the project, but it's a very recent concern in the last 5 or 10 years. We really started the project so that we can enable academic projects and projects back in the Navy government labs where I came from. But industry is an important result of this software, as we'll see. So what we want to talk about is what are the other issues that are in this equation? Because for a software project to be adopted by industry or anyone else, the source code, putting the source code online and making the source code available is really just the beginning. It's a necessary but not sufficient condition. Same with the software license, but we want to talk about some of the other things. Just to give a little bit of context, that the intro on me was a little bit old by a couple of years, maybe. I used to belong to the MIT Laboratory for Autonomous Marine Sensing Systems, which was Hendrik Schmidt's lab. We now call ourselves the Marine Autonomy Lab, and this is mostly since Henrik retired in 2023. I was a member of that group when this project started. After Hendrik's retirement, we morphed the lab to call ourselves the Marine Autonomy Lab, which is due in part because we focus mostly on autonomy software as the central component, although we are involved in a lot of other things. We are situated at the MIT Sailing Pavilion since 2011. We're part of the Department of Mechanical Engineering and the MIT Center for Ocean Engineering, and our primary research focus is on autonomous decision making. The bottom left there is what it looks like in our physical lab, and that's the dock on our right. And those are some of the platforms that we work with, both surface vehicle and underwater vehicles. Besides myself, I work with 3 other excellent research scientists shown in the upper left, and I have 6 current graduate students and a number of students that graduated recently, and where they've gone is shown on the bottom. So we're not a big group, but we're not a small group either, and we have a lot of diverse talent. And I'd say, as far as MIT goes, we might be a little bit top heavy in the sense that we have 5 research scientists in our group, whereas a lot of groups may have 1 or 2 postdocs. We have a lot of long-term talent in our group. We do work with underwater vehicles as well. We're not here to talk about that necessarily today. Most of the time we develop autonomy software, but sometimes we need to develop our own platforms to fill the gap of what's available commercially. In our lab, we've developed an AUV called the Spur Dog in the upper left. The Sea Beaver in the bottom left is a platform that we've also developed with Dr. Supan Randeni and Mike Sakarni, and it's now part of an undergraduate class that we teach as of spring 2024. And this is a short video of the vehicle in operation. So this platform is brand new to us, and it's quite a development from our lab. Historically, we've worked with commercial platforms that are much more expensive, and there's repercussions from having a low number of vehicles that are very expensive in terms of the access to the students. So being able to teach this class around these vehicles, we're able to get students involved much earlier in their education around unmanned robotic platforms. So we teach this class which is explicitly for first-year students at MIT. And we've been teaching this will be the 15th year we teach MIT Marine Autonomy Sensing and Communication, MIT 2680. So that's a little bit of context about who we are, but I will say right up front, that's also part of this equation, right? So when I say that there's more to adopting code than just getting access to the source code, a big part of that equation is the community. Is there a group of users out there that are actively using the code and contributing feedback and results is their documentation. We have many years invested in the documentation for those applications. And because we teach this at MIT, there's training material also associated with the source code. So those are actually pretty big factors in the equation. So what do we mean by autonomy? Some of the people who might be logging in are here to learn about maybe intellectual property issues and not necessarily experts in autonomy. So we'll ground ourselves for a slide or two. Some simple missions when we think of autonomy. Classically, a vehicle executing a lawnmower pattern to survey a search area. This kind of mission is, I would say, barely autonomous in the sense that it's all pretty much determined once the lawnmower pattern is determined. And then on the right is a slight variation where a vehicle is also going around on a pattern, but is using some sensors to detect obstacles. This is a simulation. In this case, it's simulated LiDAR sensors, figuring out where those obstacles are and adjusting its pattern. Those are some of the simple cases. And I would say in this scheme of things, there's probably different levels of decision making. The path planning, the generation of the lawnmower patterns, we would say is sort of a part of the mission. Path planning part could even occur before the vehicle is launched. All the way over on the right, control decisions. Ultimately, this vehicle has to decide how fast to spin its thruster and how much it should turn its rudder to be able to execute the commands. In between is where we believe autonomy lives, which allows us to sort of execute the plans and interface with the control system. And it's really where things get interesting for us. There's been sort of an evolution over the last 20 years where missions have gotten away from sort of scripted missions on the left to these coordinated multi-vehicle adaptive autonomy missions we like to loosely refer to as swarm autonomy. And there's some examples in the simulation up above. In the middle, we have a number of vehicles that are encircling a region of interest. And as they detect some sort of intruder or something of interest, they go off and explore that through an inter-vehicle auction and then return back to their environment. And the one on the right, we use Voronoi-based methods for vehicles to go off and collaboratively search a large area based on a modified Lloyd's algorithm, which is based on Voronoi diagrams. So roughly speaking, over the last 20, 25 years, we've seen a pattern migrating to the away from the sort of scripted single vehicle missions to these multi-vehicle missions. And this is an example of two things. One, it's an example of multi-vehicles doing a collaborative decision-making here. This is a exercise in Louisiana a few years ago where the vehicles are deciding amongst themselves the proper ordering before they form a linear convoy. It's also an example of how we work with industry. So this is using MIT code embedded inside of a company's code delivered to a government sponsor. So we'll have a lot more to say about that in a moment. So I would say, in addition to the items we mentioned above, open source code has to have some sort of advantage. There's a bit of a secret sauce that is involved here, and we'll talk about that in a second. But first, we're going to just sort of lay out our project by numbers, just to give you some more context. 20 years we've been online almost since 2006. I think we first advertised in 2007. Our software has been on at least 50 distinct robots that we know of, probably closer to 100 or more. Mostly we work in underwater and surface vehicles, some ground and air platforms as well. For those of you who like to measure in terms of lines of code, about almost 250,000 lines of code and about 125 distinct software modules. The economics are sort of in the green box. It's about 60 work years of development effort for this code. Spread over developers, almost $20 million to cost to develop, according to the slot count code analysis. And if you were to try to recreate that code, the estimate is about 28 developers working 3.5 years. We have a number, we put this in the economic box because the documentation, it takes a long time to develop as well. And the labs and training material are also substantial investments of time and energy and is a part of the equation. We've been teaching this for about 15 years. There's 11 or 12 companies that I know of that have adopted this code on some form or another. And one of the questions we like to ask ourselves is, why would a company adopt open source code? The short answer is economics and speed to market. Some companies are just focusing on different things, and they don't want to reinvent all that autonomy software. And so the 60 years and $20 million of code development is substantial to them. Some of the hidden things are maybe not so obvious. The pipeline of new hires from MIT, all of those students and people who have come out of our labs and are working in companies that use the code, they're all able to go to other companies and create a pipeline of new hires for people trained in this software. And as companies have this as part of their core autonomy code base, there's a certain level of interoperability with others in the community. And software components that are added onto our software are also licensable and become other sources of revenue for companies that have invested in the software. And so the software is also extendable, and as I mentioned, with the proper licensing, it could be a source of additional revenue for companies. So let's talk about autonomy again for a second. If we want to back up and just draw a sort of a high-level description of what it looks like in terms of an autonomous surface vehicle or any autonomy system, there's a lot going on. It's one of the most multidisciplinary areas that you can involve yourself in at MIT. There's path planning and mission planning. There's control systems, underwater communications, environmental monitoring, sensor processing, sensor fusion, SLAM. There's so many things going on to make an autonomy system work. So in addition to the middleware and autonomy architecture, which is really what MOOS-IVP is, there's this huge ecosystem of software that needs to exist before you can functionally operate an autonomous vehicle in a mature mission type. So I mentioned that because there's a lot going on. In addition to the autonomy software itself, every one of those autonomy applications has corresponding documentation. I would roughly estimate that for every 10 hours of time developed writing software, there's at least 5 hours invested in the documentation. And documentation is different than training material. Documentation just tells you what a module does. Training material tells you how to go from being a novice to an expert. We have that kind of documentation as well. We've also started to organize our code base in terms of example missions. Here's a couple example missions. It's another way to learn. It's another way to learn about the software is to look at a fully functioning mission and look at the modules that are involved in it and how they operate, make it available to the public. All of these things that you see here, or at least the one on the left, I believe is available on GitHub. It's just another way to engage with the code. And so all of that ecosystem is important because it's part of the story of where we were and where we've gotten to and what brought us here. So when I first arrived at MIT in the early 2000s, it was not uncommon for every PhD student to pretty much build the entire software system themselves because they were always reinventing the wheel. And it also meant that they didn't get very far. They would probably spend the first 3 or 4 years of their PhD reinventing all this software simulations, control modules, mission planning, etc., and spend the last 6 months to a year doing the interesting thing for their PhD work. So the things that I think motivate a student to adopt this code are the same thing that motivates a company to adopt the code, is that it allows you to leverage a lot of things that you don't want to necessarily rebuild and get right to the point of the thing that you're trying to do that's special. Whether it's a PhD student writing a PhD thesis or whether it's a company trying to compete in the marketplace. Quick review of the timeline starts with myself and Paul Newman. Fortunately, we were office mates in 2002. Paul had written something called MOOS. I had written something called IvP. We turned it into a project for marine vehicles. We first put it on open source in around 2006. This payload autonomy paradigm that we use was also invented around that time. And on the top level, you can see some interesting events in terms of funding that had a huge impact on our system. And as you can see, more and more as you get further in time, there's more available to students as they adopt this as a research focus area. And so what that means is that students are functioning at a higher level sooner and able to do more interesting thesis work. It also means that the number of people that are involved in our field is also expanding as well. When I first arrived in the early 2000s, it was really only the faculty and maybe a postdoc or two, in this case Paul Newman and a couple others, that were allowed to even touch the vehicle because they were $500,000 vehicles and the source code was not maintained in a way that allowed for collaboration like we have nowadays with things like GitHub. So we were every step of the way, we were able to involve first, expanding from postdocs to our PhD students. Then eventually our master's students were able to work with this as part of their master's thesis, and then ultimately undergraduate students who were interning with us. And more recently, in the last couple of years, we've had undergraduates now that can take classes in marine robotics and actually have a platform of their own as a lab partner that they can apply this software on, which is a world of difference between 20, 25 years ago when there was only one or two vehicles in the lab and they were $500,000 vehicles. These vehicles that the students are holding there are represent about $3,000 worth of parts. And we made 10 of them for teaching that class. So all along the way, we want to expand the access to the technology to more and more students earlier in their career and give as much of a head start on the components so that they can focus on esoteric things like a student wants to maybe build a buoyancy engine for an AUV, right? In years past, you'd first have to build a vehicle and then focus on the buoyancy engine. Now we have a student can grab a vehicle from the shelf and work on a special project. So, what is the secret sauce again in terms of autonomy software? So going back to this picture, the red box there is the autonomy component. So even though there's multidisciplinary aspects of this, we mostly focus on autonomy software. And so for us, what's in that autonomy box? It's something called MOOS-IVP. And MOOS is a middleware that allows applications to talk to each other through a publish and subscribe architecture. So the Helm is a MOOS app that also contains its own behavior-based architecture. So ultimately, at the end of the day, the Helm, about 4 times a second, will read mail from the MOOS-DB and post mail back to the MOOS-DB. And in between, a behavior-based architecture will make decisions about what the vehicle is supposed to do next. And so you can also look at it from this case. There's 2 architectures sitting side by side with MOOS-IVP. The MOOS-DB is a publish and subscribe architecture, which allows apps to talk to each other by simply declaring what the information they want in subscriptions and publishing mail as well. And the Helm allows behaviors to be coordinated through each other using IvP, which is a form of multi-objective optimization. In both cases, the secret or the advantage here is that the autonomy system can be built up module by module, and the architecture doesn't need to change as we swap in new apps or new behaviors. Publish and subscribe architectures are fairly straightforward, and MOOS is not the only middleware out there. There's also ROS, LCM, DDS is another one that's very prevalent in the world today. So publish and subscribe architectures are not terribly hard to understand. How you get behaviors to coordinate with each other is non-trivial, and it's kind of unique to our project, and we'll have more to say about that in a second. But the goal is the same. We want this modular architecture. So when it comes to IvP behaviors, they produce something called objective functions, which is essentially a utility function or a mapping, if you will. All functions are mappings. In this case, the mapping is from candidate heading and speed or heading and speed depth maneuvers and some sort of utility or a value for that maneuver with respect to other maneuvers. So IvP is the MIT developed model for representing and solving multi-objective optimization problems. And if you want to look at it from another perspective, behaviors produce these heat maps, if you will, or objective functions shown there on the bottom. So in our case, IvP is a piecewise linearly defined objective function, which sounds like we're down in the weeds here, but this is actually really key to everything we do and underlies this talk because it's these piecewise linear objective functions and their sort of generic way of representing utility functions, which allows behaviors to have a very clean interface to each other that doesn't rely on the complexities of the behaviors. So if we want to have an autonomy architecture where we can add new behaviors and students can add new behaviors and companies can add new behaviors, getting those behaviors to cooperate is critical. And how we get them to cooperate is we created a mathematical model where the behaviors produce this generic data structure that allows new behaviors, regardless of where they came from, to play with each other outside the box. So that's really important to us. And so going back to this Joust mission on the left, where we have a number of vehicles sort of driving through the center and testing their collision avoidance, this is what it may look like if, I think from the perspective of Cal, the blue vehicle. Let me see if this is going to play. There we go. So the timing's a little bit off here, but as Cal goes through, it's generating objective functions for collision avoidance with respect to the other 3 vehicles. And the multi-objective optimization finds the best heading and speed with respect to the weighted sum of those objective functions, and that's the trajectory of Cal as it goes through the field. And if you wanted to see maybe what it looks like if those objective functions were to be sort of summarized with their weights on top of each other, again, this is from Cal's perspective. That's what the collective objective function looks like. So that's what IvP is in terms of the MOOS-IVP half. And again, it allows us to have multi-objective optimization gives us good decision making, especially when it comes to complex decisions with multiple vehicles as we approach swarm. But also the behavior-based architecture is very extendable. So this allows us to have students and other companies and other entities write their own behaviors and add it to the system. Okay, so that's the summary of what goes into the open source code. But what about suitable software licenses? So what is a good open source software license? So going back to this for a second, MOOS and IvP are both architectures that have plugins. I just want to do a sound check to, just paranoid here that you guys can all still hear me. Can someone just tell me that you can still hear me?
We can hear you well.
Awesome. So this is the architecture. And another way to look at this is that each one of these apps and behaviors has a sort of a generic component and a special component. For each MOOS app, there's a MOOS app superclass, which handles all the mail handling and things like that apps are required to do to sort of plug into the system. And all of that is under an LGPL license. And the special features of that app are under a GPL license. Same with behaviors. There's an IvP behavior superclass. There's also geometry libraries that a lot of behaviors like to link to. Those are under LGPL licenses and a GPL license for the specific code. And what that means is that the app itself is protected under a GPL license. But if someone wants to write a new app or a new behavior, and all they need to do is link to the MOOS app superclass or the IvP behavior superclass, they can write their own proprietary classified or special behaviors or MOOS apps of their own, and everything's just fine. So if a company wants to come along and take the MOOS-IVP code and represented in blue here, a company wants to add their own apps and their own behaviors, they can basically create a hybrid system where they have a partially open source code base with proprietary code base layered on top of it. So that's how we handle the licensing in general for MOOS-IVP. What about how do we need a commercial license, which is really the open question going into this conversation. So another way to look at the code is that there's on the left, there's this sort of layered hierarchy. There's the MOOS middleware, the MOOS-IVP code with the IVT autonomy on top of it. We do have another software toolbox called the Swarm Toolbox that we're working with the MIT Technology Licensing Office to distribute. And then industry users basically write their own apps and behaviors to develop whatever it is that they're interested in doing. And we go back to the C-Train demonstration again because all of these vehicles are essentially structured with the code base that you see on the left. So what does it mean to have an industry partner? So there's a number of different industry partner arrangements that I bumped into, and this is my own personal reflection. Some of this has grown, and some of this might still grow. But one type of way of looking at this is that MOOS-IVP as an open source autonomy project out of MIT can be adopted by a robot company. We'll call it Acme Robot Company. And this company might be developing their own platform. In some cases, the platform is the company in the sense that their secret sauce is a unique physical platform, whether it be an underwater vehicle, amphibious vehicle, or surface vehicle, etc. And their secret sauce is all invested in the hardware, and they need an autonomy system, and they don't really want to spin up a whole autonomy group to do that. So they will adopt the MOOS-IVP code. In some sense, it becomes sort of like an OEM software code base. It's not something that they advertise as being part of their company, but nevertheless, it's part of their code stack, and they might develop their own code on top of it. And in the simplest case, these companies are essentially just doing research. They're getting money either through the government or SBIRs or through venture capital. They haven't sold anything yet, but that's their current state. And there's about 5 or 6 people that we work with in that fall into that category. Another category is when there are companies that are actually selling these things to customers, and we work with some companies that fall into that category. So they're writing their code. They're pulling in the MIT code, they're building their vehicle, and they are delivering a full system to a customer, which includes the boat, which also was developed by the robot company. So that's an interesting category. Another category is rather than Acme Robot Company, it's Acme Autonomy Company. So they are building autonomy software or kits that can make other people's boats autonomous. So they may not be delivering a full autonomous system to a customer, but the customer may be have their own boat or have their own relationship with a boat builder, and they're providing an autonomy system and using their boats in that manner. And then another category is perhaps where Acme Autonomy is not working with the end user directly, but actually supporting a prime contractor. And the prime contractor pulls in Acme's code base as part of their system, maybe other technologies, maybe a boat from a boat builder, and they're providing a system to an end user. Right? So um, all of these arrangements are representative of companies that we're currently working with. And in this case here, this is kind of maybe the more mature model. And we're involved with at least three companies right now that are delivering what we call program of record or platform of record systems to the Navy. And so it's quite different than the companies that are just building research prototypes and need an autonomy system. But it's interesting to think about all of them. And I think overall, we're probably working with a dozen companies, and there's a few companies that I think we're in the conversations with. And part of the conversation is how we are handling commercial licensing and IP. So it's a very relevant conversation to us. So um, in a situation where a company is developing code and they are developing their own applications and their own behaviors, it's a relatively straightforward process for us, right? Because we have this LGPL and GPL relationship. So they write their own apps, their own behaviors. It's part of the Acme code base. The OEM autonomy or the MOOS-IVP autonomy from MIT doesn't change at all. It's a very clean situation. And for the most part, I think companies that are operating this way don't feel like they need any kind of further commercial license or clarification. In some cases, I could be wrong. In some cases, the companies I think may have very conservative legal team and are still interested in a commercial license anyways, even though we feel like the LGPL and GPL arrangement is sufficient. There are still concerns that sometimes people have, and we're trying to sort through what they may be and try to address those through a commercial license. Where things get a little bit more interesting is when a company does all of the above, but also for whatever reason or another, they need to be able to take one of the apps that are distributed by MIT or the behaviors, and they need to augment it a bit. So now it technically becomes a derivative work. It now technically, if the GPL, if it's under GPL, they're required to release the code, or at least they feel like that's a possibility that they might have to deal with. Sometimes that modification might be something really simple, like an app or a behavior needs to expose another configuration parameter that's already there, but they just would like the ability to configure it. Or it can actually change the function of the apps or behavior and become sufficiently better, or it may address a bug. We like to engage with companies so that if it is a bug or if it is a feature that we'd like to work back in the system, we can avoid this situation by just accepting a pull request or a suggestion on how to fix the situation and go back to the situation where they don't need to work with a modified app, a modified behavior. But not all companies work that way. Some companies we don't have relationships with, they're working on their own. They don't feel comfortable putting up pull requests. For whatever reason, this situation comes up a few times. So then the question is, do we need a commercial license to address this? And what does that commercial license look like? Right? So going back to this situation here, what does it mean if Acme code somewhere along the way, or the prime contractor somewhere along the way, is modifying what is ultimately began as something out of the MOOS-IVP stack under a GPL license? What does that mean in terms of their obligation to make those changes available to the public? And to what extent do we at MIT care, right? So if it's something simple like exposing a configuration parameter out of convenience for them, that's really not that big a deal. But if they are making modifications to modules that essentially become now competitors to what's coming out of our lab, then now we basically have a bifurcated project or a bifurcated situation where some people are getting their MOOS-IVP from Acme Autonomy and some people are getting it from MIT. That's not happening yet, but we'd like to be able to be sort of eyes wide open about how to avoid something like that. So that is our where we're at right now. That's a 25-year history. A lot invested to get us here at this point, and we're super happy to be working with folks from industry. And I think our big to-do list on the item right now is to work out what it means to have a commercial license and how to better support the industry for the folks who need that. And I think that brings me right up to the end of my time. So I'm happy to take questions if anyone has any.